Hello geometers and seekers of truth. In this video we are going to demonstrate a fairly famous and significant theorem in geometry. It's called the triangle inequality theorem. And it says simply, in any triangle the sum of any two sides is greater than the remaining one. So if you take any of the two sides and add them up, it's greater than the remaining one. Now, for two of these cases, it's almost obvious, so we're going to skip it, okay? But there's one case that is a little bit trickier. So suppose you have one of the sides is the longest one, so AB. We have to demonstrate now that the two smaller parts added up will be larger than the largest side, okay? And let me give you some implications for this. So let's say you had like a triangle that was very, very weirdly shaped. Okay, so it has this long side here, and then let me change colors here just so that you see a little bit better. Whoops. So let's say you had this very, very long side here, and then you had, this very slim path, right? This red path here, and the question is it possible for the combination of these two red paths added up to still be smaller than the blue one? Okay? And the claim here is that no matter what, in order to make a triangle, the two smaller sides combined have to be larger than the largest side. Okay? So the two smaller sides combined have to be larger than the largest side. And that's what we're going to show here. And we're going, so let AB be the greatest side of triangle ABC. We want to show that A plus AC, that's this length right here, plus BC would be greater than AB. Okay. Now there are many different ways of doing this. What I'd like to demonstrate here is a process that what Euclid did, which is using as little information as possible. I've seen work here that uses the Pythagorean theorem and the hypotenuse and right triangles, and those are pretty nice, but we don't know the Pythagorean at this point in our study, and we haven't really proved it yet, so we're going to rely on what we know so far. Okay, so we're going to do this. Let us take AB, whatever that length is, and we're going to extend AC by the exact same amount. So whatever that length is, we're going to extend it by the exact same amount. We're going to extend AC by the same amount. Oh, I'm running off the page here. Let's name this point here D. Okay. Then we're going to join D to B. Okay. And what I have now is essentially three triangles. There's the original triangle, ABC, that I was working with. There's the new isosceles triangle that I just created. Okay, and then finally there's the big triangle ABD. That's the combination of them. And using the interplay of these three triangles, I'm going to demonstrate to you why this statement must be true. Okay. So similar to what I've done before, I'm going to try to color code this so that it's easier to follow, and then we'll write it up. So you have an isosceles triangle here, BDC. So that means this angle here and this angle here, the two angles in green, they have to be congruent to each other. Okay? Next, let's see, different color. Let's go with purple this time. The other thing I know is that this purple angle here must be larger than the green angle. Okay? The purple angle here must be larger than the green angle. Okay? And so the purple angle here must also be greater than this other green angle. The two green angles are the same. The purple angle is greater than one of them, so the purple angle is greater than the other one as well. Okay, so let's write up this detail so far before we get too lost here in the picture. So what would we do? We extend AC the same amount as BC to make CD such that it's congruent to BC. Okay, so that's what we did here in the first line. Okay, and then simply join D to C. And then we can make this claim: since triangle BCD is isosceles, then angle CBD is congruent to angle CDB. Okay? And this is proposition 5, okay, or the base angles theorem. Okay. And then the next statement here is that the purple angle is greater than this green angle. Purple angle is angle DBA is greater than angle CBD. This is common notion 5. The whole is greater than the part. And so, using statement 3, DBA, or angle, excuse me, let's see, erase, yep. Angle DBA is also greater than angle CDB. That's the other green angle up here. Okay? So statements 3, 4, and 5, they say the following: the two green angles are the same. The purple angle is greater than one of the green angles, so the purple angle is greater than the other one. Okay? Now here, we are almost done. If you look at step 5, and if you look at the big triangle for a minute, since the purple angle is greater than this green angle, let's see if I can use my color coding to help illustrate. The purple angle is greater, so this line segment right here must be greater than this line segment right here. Okay. So if you look at the big triangle, DBA, the purple angle is across from the purple side. This green angle here is across from this green side. The purple angle is greater than the green, so the purple side is greater than the green side. Okay, so, and we know that this must be true from proposition 19, right? That's what we just proved before. So since DA is across from DBA, and AB is across from CDB, that's the green angle, DA is greater than AB. Okay. Now, what we're trying to show, right, is what we have here in red, and what we got to is what we have here so far. And so we're pretty close. We're almost done, right? So we just have to kind of unpack DA here. Well, what is DA made of? Well, DA is nothing more than DC and AC. Okay. This purple line is just DC and AC. But DC is the same thing as BC. Right? And I'm just going to highlight this for understand, for maybe to help you visualize a little bit better. But DC is the same thing as BC. Right? DC is this green one right here, and BC is this one right here. So that tells us that BC can be replaced can be used to replace DC. Yeah. And I need to put in some reasoning in here. So let's go back a little bit here. This statement here, number 6, that comes from Proposition 19. Whatever is across, whatever angle, whatever side is across from the larger angle is larger. And then from here, when I separate DA and AC, this is common notion 5, which deals with the wholes and the part. So DC and AC are the part. Together, they combine to make the whole. And going from DC to BC, that is common notion 1. Whenever you, or the substitution property is the other name for it, but I'll write it here in Euclid's words that, like, because BC and DC are equal, we can switch one of them for the other without changing the meaning. And thus we have done it. We have demonstrated using this picture that the triangle inequality is true. Like, whatever triangle that you make, the two smaller sides added up must be larger than the largest side. Yeah. This has great implications. It can be used to prove some fairly significant things, like the shortest distance between two points is a straight line. It can be demonstrated to prove certain facts about physics and optics. Okay? But we'll save those details for another day. As always, keep working hard. Thank you for watching, and have a wonderful day.